Please feel free to let me know if you need anything, if you have suggestions about the workshop. And so our first speaker today is Professor Samuel Mathur from Ohio State University. And he's going to give us the introduction, an overview of the information paradox. So that's the only session this morning. Please feel free to ask questions. Let's welcome Professor Mathur.
Okay, thank you. Thank you for the invitation to come to this very nice place and for organizing this workshop. So this first talk is just meant to give you an introduction to what the paradox is. And even though everybody has heard of Stephen Hawking and the fact that he found this very amazing paradox, people who don't actually work exactly on this problem sometimes don't quite know what the puzzle is. And so that's completely fine. This talk is meant to introduce you to the puzzle, starting from completely first principles. And this will work best if you keep asking me questions continuously. So every time I say something, you should stop me if you have a question, and then we shall have a discussion. Okay. So I'll try to do this in small steps. And so let's start with step A. And so first, we'll see what is the source of the entire problem. And the source of the problem is something very basic, and that is that gravity is attractive. So we all know that in gravity, two masses will attract, while if you take something like electrostatics, then like charges will repel. Okay, so that is something very basic, and that is the source of all the problems. So let us see how that happens. So suppose you have some mass here. Think of it as some heavy mass. So I call it capital M. And then here I will place some test mass. So it's some small mass, test mass. So I call it little m. And I ask what is the energy of little m. And so I try to write the energy of little m. So let me call that Em. So if I only had this mass and I don't think about this, then this mass has an intrinsic energy, mc square. So Einstein told us everything has energy inside it, mc square. But because this is also kept somewhere near this guy, and let the distance between them be called r, then this will also feel some gravitational potential energy. So let's just make some heuristic approximation and just see how do we write the total energy of the mass. This is the intrinsic energy, but then I should also add the gravitational potential energy, and that looks like this. So I'm being very schematic, so maybe I can just put some schematic symbol because we are just talking about rough ideas. So this minus sign, that is what corresponds to gravity being attractive. So everybody is familiar with that, I suppose. And so now if you look at this formula, you see something interesting. If I keep making r very small, at some point this will actually become 0. So let us see when it actually becomes 0. So if I put this equal to 0, then the little m just cancels out, and you find r is equal to gm over c square. So if I place this at a distance which is, let me draw here the radius gm over c square. If I place this test mass inside that radius, then the total energy of this mass will be negative. Okay, so let me write that. So for r less than gm over c square, the total energy of m will be negative. So you can see that is a problem, because if the total energy is negative, it means the theory is unstable. It means you can make the particle for free. Because if you make a particle in empty space, it costs you energy mc square. But if the energy is not mc square, you try to create it here, it's mc square minus something. And if you try to create at this boundary, energy is 0. So the energy is 0, it's free. Okay? And so because here it is negative, the theory is unstable. Okay, so this tells you, so at the conclusion here, any theory with gravity is unstable. And this is essentially all there is to the paradox. It is such a robust problem because we have hardly used anything about the theory. We all know gravity is attractive, so I put the minus sign. And we haven't had to use any GR or any quantum mechanics. All that will come in only to make the problem more precise. But the essence of the problem is that any theory with gravity seems to be unstable. It looks like you can create particles from nothing. Okay? So let me just pause here for a second and see if there are questions. It's really just to get you starting to ask questions. Does anybody have a comment on this? This was my part A. Yes.
I'm wondering, is this configuration an allowed configuration from some sensible initial state? Because, for instance, as you said, you decrease R, but if I throw in some particle from the outside, even after it falls in the horizon, it still has positive energy.
That's an excellent point. And I will actually come and talk about that in a minute.
I see.
Yes. So that's a very good point. Right now, the question here was, let me repeat the question because it is actually very crucial. The question is, can I really create this situation? Can I really put this particle so close to this? I'm saying that you can put it, but how do I put it? Maybe we have to think about it. And it is actually going to be important. Okay. So I'm going to store that question. So sometimes I'll just store questions on the side. So let me write the question here. How do we create it? How do we create that? If I cannot create that configuration, then of course I don't have a problem. Create this configuration. And you're right, if I cannot create it, then there is no problem. So I'm going to store that question for later. More questions? Yes.
There's a old calculation, before general relativity, where, who was this guy? Mitchell, I think he said, what would be the mass of a star if the escape velocity is the speed of light? And then he equated half mc square with gm by r and precisely got the Schwarzschild radius.
That's right. Yeah.
Right. So, but ignored the rest mass in that because relativity was
mc square. Yeah.
Is there a connection for this factor of 2?
Yeah, so here the factor of 2 was not supposed to be precise, which is why I put this. Because if you use mc square, you are using special relativity. If you use this, you're using Newtonian gravity. But if you have relativity and gravity together, you're always supposed to do general relativity. So that way, this was not supposed to be a precise statement. The Mitchell's thing actually just, I think, was more of a coincidence because he also doesn't have the Schwarzschild metric. So I don't know how to make sense of the fact he got the exact factor correct, but I don't have a better answer than that. Yeah. Okay, so let me go to step B. So as we were just discussing, this is very heuristic because you used relativity here, special relativity, and then you used gravity, but relativity and gravity together should make general relativity. So we're now going to talk a little bit about general relativity. And so why do we need general relativity in all this? Well, the first thing is you have to ask, how come we don't have this instability everywhere around us? Like, how come we don't have this problem before? It's such a simple problem. Why hasn't it been bothering us before? And usually the problem is that the mass is usually not so dense. Yes. Yes.
Say the same thing for Coulomb force. In that case, the QED was safe because of minimalization effect.
Because of?
Minimalization.
Yes.
Yeah. So maybe what you want to say now is that this, in gravity we cannot normalize, or we don't know how to normalize.
Yes. Let me say something and then come back to ask you again what you were saying. I'll ask you to make it more precise. If you have electromagnetism, the big difference is that if you try to put lots of positive charges together, then you cannot do it because they repel. So you can just make maybe one proton or one electron. If you just have one electron, of course, then this distance will be very small because there's hardly any charge. The distance will be very small. The Q will be very small. And then, of course, you'll be caught up in the all the quantum effects. It's within the quantum. Yeah, well, even before that, the quantum uncertainty, you can't even come that close. You cannot make R very precise because the wavelength of the particle you bring will be a little fuzzed out. So then the question is, how does the proton or electron itself exist? Like, that is renormalization. How do you have a point mass which has some charge? And there, of course, you have to go to renormalization. But even if you renormalized one particle, the reason you cannot actually make something classical, the whole beauty here was you could take this mass to be very big. We'll think of this mass to be like one solar mass. Then this distance is like 3 kilometers. I don't have to worry about any quantum mechanics. And that's why the problem is so robust. If I could only make it like 1 electron worth of mass or 1 electron worth of charge, then so many quantum things happen, I cannot make such a simple argument. So here the point is, I cannot actually put all these charges together without the energy becoming too much. It's not clear how I will do that, right? But in one sense, it is completely true. If you put a lot of charges and suppose you force them to come together, you can do that. And suppose you make the charge to be bigger than 137, which is 1 over alpha. Actually, the same effect happens here, which is like the Hawking effect. You get Schwinger discharge. So I'll talk about that again when we come. So let me just save for myself another question. I'll come and talk about the Schwinger. I'll mention that, but at that point you should ask me the question again, because even though you get a Schwinger process in this case, which is sort of like Hawking radiation, which we will discuss, it doesn't create the same problem. And so that I will have to give you the reason. Okay. So very pertinent question, but again, I'm saving part of that question. Is there any more questions? Okay, so let's go to step B. And so the point is, how come we normally don't face this with the Earth? So if you take the Earth, then the Earth itself has some radius, which I'll call r, and it has some mass. And then the distance r, which corresponds to gm by c square, it's actually rather small for the Earth. So if once you come inside the surface of the body, the potential doesn't have this formula, 1 over r. The potential does not rise very quickly inside the Earth. Okay? It rises, but not very quickly. And so you never get into a situation where the total energy of m will be negative. Okay? So if you want to make this funny thing happen, then you have to make sure that the object is very dense. You have to sort of make it very small. So the question is, who will make it that dense? I mean, the Earth is not that dense, the planets are not that dense, so how do we make something that dense? And that is where black holes come in. So that's where the general relativity gets in, because with general relativity we find the fact that suppose you have a star, so I'll start with a star, and then the star stops burning because all the fuel is exhausted, and then it starts to collapse. And then what happens is you get a runaway collapse. And runaway collapse means as it gets denser, the attraction is even more, and then it gets more squeezed, and the attraction is more, so it just runs away, and then it goes all the way to a point. So that is okay to say in words, but the question is, why does it have a runaway collapse? Most things in nature always come to some balance. You squeeze it, and then there's pressure, and you squeeze it more, the pressure is more, so it will come to some balance. And in this case, we know it actually goes all the way down, down, down to a point. So how do we know that happens? How do we know it doesn't just stop somewhere? If it stops somewhere, then maybe I could not do this, right? So we have to understand how the runaway collapse happens. And for that, you have to look at the picture of the black hole. So I'll just try to draw the picture. And I'm sure you know this, but I'm just putting it all here for completeness. So my time direction goes here. My radial direction is like this. And this is my angular direction. And I'm just trying to make a schematic picture of what a black hole is like, which you must have seen in a textbook. And so what happens in a black hole, that if I draw the light cones, then far out the light cones just look like this. Light cones just go like this. But as you come close, so all my mass is in the center here. This is my mass m. As you come closer, the light cones a little bit turn inside. I want to draw it nicely. So it's easy to go in, but it's rather hard to go out because the light cones are a little bit tilted towards here. And then when you come to this critical radius, which we call the horizon, then the light cones become like this. So now you can easily go inside, but you can't go outside. Even if you try to go outside, at best you will stay at the same radius, the horizon. And if you go further inside, then the light cones point purely inside. Like you can go in quickly, you can go in slowly, but you cannot even stay at one place. If you stay at one place, same radius, you're already going outside the light cone, which means you're moving faster than the speed of light. Okay. So this means that once, if you have a star and the star is collapsing, it was this big, then it became this big. And once it comes to be this big, all the points on that, they have to keep going in because the light cones point inwards. Because the light cone is pointing inwards, this will squeeze further and further, and then it will become a point. So that is where we use general relativity. This argument didn't have any general relativity, so why do we need general relativity for the whole problem? We need that because we want to be sure that this mass can be made very compact. And you have runaway collapse in general relativity, and the source of the runaway collapse is the light cones turned inwards, and now it doesn't matter what force you have, you can invent. There are so many forces which might exist, we don't even know what they are, but as long as you believe that nothing can go faster than the speed of light, then once something turns inwards, it has to squeeze down to a point. So at least this thing is going to happen. So now you can see we will really get into this problem. Okay, so that was our step B. That's how black holes come into the story. Okay. Other questions on this part? So I just wanted to ask, is everybody here? Yes, please.
Can I say this is based on the belief that the Schwarzschild metric go all the way from outside to inside?
Yes. Right now I'm just using classical GR, so I'm assuming, so let me just write that as an assumption, assuming the Schwarzschild metric describes interior of horizon. That's what you were saying, right?
Yeah.
Are we sure that's the interior of the horizon? And if it doesn't describe the interior, the argument fails. So that's very important. Any one of these steps, if you can find this is not going to be true, then you solve the puzzle. Right. That's the question. Okay, so now we see how general relativity comes in. Now let's come back to the question. So now I won't always draw the full picture of the black hole like this. I will just draw the black hole very schematically. I'll draw it like this, and all the mass has gone to the center, and this radius r. If you compute with proper general relativity, there's an extra factor of 2, as Shumit was just noticing, and instead of getting gm by c square, it becomes 2gm by c square. Okay, but that's why that argument was very rough. If you do it properly, qualitatively, it's the same argument, becomes 2gm by c square, and we can call that the Schwarzschild radius. We can call it rs, the radius of the black hole. Okay, so for a solar mass black hole, that is about 3 kilometers in radius. So I just wanted to ask, is everybody familiar with a little bit of general relativity and some quantum field theory? Can we just assume that? We don't need any string theory or anything for this talk, but at least those I will just assume. But again, nothing very deep from there. But if you have a question about something there, you should feel free to ask. So this looks okay to everybody? Okay, so now let's ask the question we had before. So let's go to step C. So here now I'll draw the same picture as this. If a particle is out here, this is my test mass m. My total mass of the black hole is capital M. If m is outside here, its total mass is positive. Here, its total mass is 0. But if it is here, the total mass is negative. Okay, so same puzzle. And in general relativity, you can then go and prove that very properly. You can show that inside the black hole here, you can actually give a particular 4 velocity to this particle, such that the energy of this particle as seen from infinity is actually negative. Okay, so the energy as seen from, so this statement we made, this looked like a very crude kind of statement. It has a very precise form, and the precise form is that the energy of the mass as seen from infinity is minus, there is a killing vector, which I take k mu, and this is the 4 momentum of this particle. So every particle in relativity will have a 4 momentum. K mu is the killing vector, which at infinity is just time translations. Okay, so at infinity, the killing vector is just d by dt. You can continue that inside in the complete extended Schwarzschild diagram. So the killing vector continues everywhere. And then that killing vector everywhere is called k mu. If you dot k mu with p mu, that's the mass of this particle as seen from infinity. What that means is if you put in a particle with that much 4 momentum at this position, then seen from infinity, the mass of the black hole will change by this amount. And then you can see from there, if you put it here, the mass will increase. If you put it here, you can choose p mu to make the mass 0. If you put it here, you can choose p mu to make the mass negative. Okay, so it's all whatever you were saying roughly, you can say it precisely. Okay. Okay, but now the question we were asking was, how do we actually put the particle there? So this one we don't bother about. We want to put it there, and then we have all the fun. We get a particle for free. But how do we put it there? And if you try to say, okay, I'll just start with the particle here and let it fall in. How about that? So actually that doesn't work. So why doesn't it work? Because this was only using the intrinsic energy, which is always there, and then the potential energy, the PE, that's negative. But if you drop the particle, it has the intrinsic energy, it has the potential energy, but it also gets some kinetic energy. So now it has three kinds of energy. If you add all three, actually the total is positive. It's not negative. And the reason you can see it's positive is that when you start at infinity, of course it is positive. There's no potential here, no kinetic here, and mc square. But as you fall, the energy of the particle is conserved. So even if it gets here, it will still have the mc square, it will still have this, but it will also have kinetic, and all of them will add up to what? Back to mc square, because that was the value at infinity. So throwing from infinity is not working. Okay, because getting is exactly what you were saying, so that it had kinetic energy. So let's see if you can be more clever. You can maybe tie a little rope and put the particle on the rope and slowly lower it in. Then you extract the kinetic energy, right? Then the kinetic energy will be sort of zero by the time you get here. You can make it not have any kinetic energy. And the potential energy still becomes like this. And you can actually make the energy of it zero. If you lower it like that, you can actually get zero energy by the time you're here. But actually you can't take it inside. If you look at the diagram we had drawn for the black hole, once you're inside the horizon, the particle has to keep falling. You can't hold it at one place. Okay, so it will keep falling. So you can get zero, but you can't get negative. Okay, so somehow we are still not getting all the fun we wanted. This looked very interesting because it looked like we could make negative energy very easily, but right now we have not quite succeeded. Okay, and this is going back to the question you had asked. But this is when we get to the third step, and the third step is that actually the particle can be created inside, and actually it's created automatically. We don't even have to do it. And the reason it's created in that place with the correct 4 momentum to make it negative, this E negative, it actually happens because of quantum mechanics. So this is where quantum mechanics comes in. So let's see how quantum mechanics comes into the story. So if you have no black hole, nothing, then the vacuum always has what we call vacuum fluctuations. And that means that from the vacuum, you can create an electron and a positron pair, and they will last for a short time, and then they will annihilate again, and they will disappear. So empty space, a pair comes out, then it annihilates again. So this is just normal quantum field theory. Can I assume people are familiar with this fact? Vacuum is fluctuating all the time. So how long does this pair last? How much time does it last? It sort of decays quite fast. Well, the energy of the pair is, let's say, 2mc square. So that's the extra energy above the vacuum. The vacuum has zero energy, but because of quantum fluctuations, it can sometimes go to a state with more than zero energy. That's a very rough way of speaking. Okay, it's actually energy eigenstate, but crudely speaking, we can assume we can borrow some energy delta E, which is 2mc square, because I create two particles. And suppose the whole fluctuation lasts for a time delta t. So if delta E times delta t is like not bigger than h bar, then the fluctuation will survive. So if you ask roughly how long the fluctuation survives, if this is 2mc square, but the time is short enough like this, then you can have the fluctuation. Okay, just a crude way of speaking about the fluctuation. So this we know, and this we have known from many sources. We have tested this in the lab. I mean, there are many effects like the lamp shift and so on, which come because of these virtual fluctuations. So quantum field theory tells us this thing does happen. But now let us see what happens if the same fluctuation happens near the surface of a black hole. So you can create a pair of particles. Let's say E minus is here and E plus is here. So you can create a pair of particles. Because this guy is outside, its energy is positive. But this guy is inside, so its energy is negative. And so total energy can actually become zero. So you can make a pair with total energy zero. And then if you put it in this formula, now delta t is infinity. And what that means is the particle pair does not have to annihilate again. The new configuration, which has one pair, one outside, one inside, it has the same energy, as the configuration without either of the particles. So that's the important step. I hope that's clear. If you have a question, please ask. So that's a free pair because the total energy is 0. Okay? And so this little algebra is simply telling you that you don't have to annihilate. You can just create the particle because this wave function can just go there. It has the same energy. So it actually goes there. And so you get what is called the Hawking process. And the Hawking process is the following. One particle falls into the hole. Once this is inside, you can assume it falls in. And this particle, it can just drift out to infinity. It's outside, so it's a wave function. It can just keep drifting. Actually, a lot of the time, it also falls in. And then nothing happens. Okay? But once in a while, because it's a wave, a piece of it can just come out. And we are interested in those guys which actually come out. Okay? So that's very important. People always ask, why can't this guy also fall in? And it can. And that's why if the black hole is very big and the attraction is therefore strong, it's difficult to get out from there, most of the particles, this pair also falls in. And so Hawking radiation for a big black hole is a very slow process because only a few of these guys are actually going to make it all the way out. But let's focus on those guys which actually come out. So the guys which come out are the ones which are called Hawking radiation. And now we have the complete Hawking process in front of us. If we have this black hole, or maybe let's go back even further, we start with the star, we collapse this, we shrink it till it's inside the horizon, then by itself it keeps getting all the way squeezed to a point. It makes that kind of thing with the horizon. We have just been drawing it like this for simplicity, and then we don't do anything. We just wait for quantum mechanical fluctuations. The fluctuations will create pairs like this. This particle will fall in. This particle, sometimes it will fall in, but sometimes it can also go out. Let's focus on the ones that come out. What those particles are doing is that they are carrying energy out to infinity. When you come out to infinity, of course, you have positive energy. So this is real radiation, carrying normal particles, carrying normal energy. And where is the energy coming from? Well, the energy of the black hole has gone down because it had energy mc square before, capital MC square, but this guy had negative energy, so total energy has gone down. So you can see how the energy balance is working. The black hole energy is going down, and this energy at infinity is being collected. So in that way, energy balance is working. So that's very important. Let's write energy balance is working. Because the particle coming out has positive energy, but because this guy has negative energy, the total black hole mass is going down. Okay? So that process of radiation is called Hawking radiation, and this is all there is to it. You can just see from here it's going to happen. So this is a very important step. This is what Hawking discovered in 1974. So let me just pause here for a second and see if there are any questions about this one. Yes, please.
In your story, and the time dependence is not important?
Time dependence.
Yes. Is not important in your argument?
So time dependence of what exactly?
Of the geometry.
Of the geometry.
Yes.
Yes. So it is not very important because the mass of the black hole is changing very slowly. So the metric is changing very slowly. And if the metric changes by a very small fractional amount, in the time it takes for one pair to be created, we can just ignore it. So I will give the scales in a little while. But as you make the black hole bigger, like if you make it solar mass, the fractional change in the geometry between before the emission, after the emission is very small. It will be 1 over m over m Planck square.
I see. So, and based on the such uncertainty relation argument, and you can apply the argument to eternal black hole too, right?
You can apply it, yes. Eternal black hole will also radiate. Absolutely. It does.
I see. But his Hawking's original paper, and he started the collapsing process first, and then apply to the curved space argument in quantum in standard quantum field theory.
Yes.
And,
yes.
So for me, and the time dependence is important to change the meaning of the vacuum state.
Okay, so let me just try to rephrase your question and then see if that's what you are saying. There are two different time issues involved. first, do I change of course, the mass of the black hole is changing because we just saw it's going down. But I was saying that the change is very small, so I don't have to worry so much in trying to make this picture. There's also, if you actually look at the Hawking's paper and the dynamical evolution in Hawking's paper, that was a time-dependent path of this particle. So he draws the paths of this particle in a more precise way. And then, of course, the whole process of dynamical collapse is very important. The black hole being made to give the Unruh vacuum has all the collapse. And I'm going to talk about that also. But that is going to be further steps, C, D, E, like later steps. So right now, we have not come to the level where we are really seeing Hawking's calculation. We are still making only heuristic arguments, right? But when we see Hawking's calculation, we'll really see where the time dependence is important.
Okay, thank you,
Good.
thank you.
Yes.
So, and just in case, let me check your statement of the energy balance is working. And energy balance means a total energy of a black hole and outside energy
Yes.
is almost constant
Yes.
in that sense, right?
That's all.
Okay, thank
That's
you.
what we mean. Yeah. And that has to be true because if you look at the energy from infinity in general relativity, you know that that energy cannot change. So if something came out of the black hole, then the mass of the black hole should have gone down. Okay. And the reason I mentioned that thing about energy is that we can come back to one of the questions about the Schwinger discharge. Okay, let's come and talk again about the Schwinger discharge. Okay. What is different about that and this case? Okay. So the difference is the following. Let me see. Okay, I'll talk about it in 1 second. Let me just say one more thing. I can use one more board here, right? So now that we are talking about the Hawking process, let us see what happens at the end of the Hawking process. What's the end of this process? So the end is that you have many particles which have come out. So this is my radiation. These are the particles which have come out. And the black hole became smaller and smaller, right? So it sort of became very small. And so in the end, Hawking assumed the black hole is completely gone. So there is nothing here, and I only have radiation. So the entire energy of the radiation, I can call it E radiation, will be equal to m. So I start with a black hole of mass m. In the end, the black hole is all gone, and I only have these particles. So this is the full Hawking process. And so this is called black hole evaporation. So this makes sense to everybody so far? So now let us ask what is the difference between black hole evaporation and the Schwinger process I was mentioning, the difference between electromagnetism and gravity. And there's the whole crucial difference, and it is going to go back to this one thing which we said right in the beginning, that gravity is attractive. The whole sign difference will come in now. So let's see what happens. Suppose you do the electromagnetic case. So let's write E and M, electromagnetism here. So suppose I have some protons here. These are protons. And suppose the charge of these, total charge is more than 137, which is 1 over alpha. Okay. Then the same thing happens. There's the electric field here, right? This electric field E. And because the electric field, there are vacuum fluctuations which create electrons and positrons. Same fluctuation I talked about there. The electrons are attracted and the positrons are repelled. So these guys, they will attract here and the energy will go down and these guys will escape. This is called the Schwinger discharge. So if you start with a nucleus of charge more than 137, which you can't really have because nuclei don't have charge more than about 92. But if you could have one, let's assume the strong force was big enough and you could have it, you can actually calculate that this process will happen. But what is the big difference? There is an important difference. You will have many, at the end of the process, there will be some positrons collected here, just like this radiation. But what will we have here? We still have all the protons, and we'll have some electrons which have come here. Okay. And they're all sitting there. Okay. And once the total charge becomes less than 137, the process stops. Because now the field is not strong enough to do this thing, 2mc square, that whole thing will not work. So once the field becomes smaller than when the charge becomes less than 137, it will stop. But look at the big difference between this and this. Can anybody tell me what is the big difference here? There is no puzzle with that. But there's going to be a very big problem with this. And what is the source of the problem? Yeah, so this guy is gone. But this guy is not gone. So this guy is not gone because obviously the protons are there, and then the electrons also came. So there are more things than before, right? So you get twice as many things. But in this case, we also had that. We already had all the mass m, which was coming from the star, and we also got the electrons. So how come the mass did not go up? How did the mass go down? And the only reason the mass went down is that it is true you had the capital MC square from this guy, and you also had the little MC square from these guys. That looks like lots of mass. But then you had the minus sign. And because the minus sign, the total energy sort of went down, 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 and the guy just vanished. Okay. So it's the negative sign of gravity which tells you that you can have lots of stuff in the black hole. All the stuff fell in there, right? And yet the total mass can be 0. And when we draw this thing properly with general relativity in a minute, you will see what configuration it is. Right now we're still being very schematic. How did the whole thing have 0 energy? We'll draw the configuration. You will see how it has 0 energy. But if the energy can be, it's again the same thing, that because the minus sign, the black hole goes away and you have radiation left. So Hawking said that the black hole just evaporates away. Okay? We have not yet come to any problem with this. Right now it just looks like an interesting phenomenon. Okay? The problem came in the next year. This was the work of 1974. Okay? And I will first tell you what the problem is, still in the schematic way. And then we will go around and see in more detail how the Hawking calculation is done. Okay, so we'll be more precise about it. Yes.
Just to make sure of the assumptions. So one assumption was that there is something like a horizon, and one of the things that horizon is doing is, what is a time-like killing vector actually becomes a space-like
Exactly.
vector inside.
Because KMU changed sign, that's why the negative sign of the EM is
There
allowed.
is nothing wrong with negative energy particles. I mean, because
Yeah,
just as there is nothing wrong with a negative momentum particle.
that's exactly right. Yeah.
And the other thing I just want to make sure is that one is able to apply quantum field theory at the horizon. Regular
Yes.
quantum field theory.
So we are assuming that the horizon is a regular place,
Okay.
a smooth place. And that's the whole thing that everybody has traditionally believed about the black hole, that when you make a black hole, we still have the picture up there. The one calculation we did not do, but let me just mention it. It's very easy to do. That time at which the star passes this critical radius, after it goes inside the horizon, we've seen it has to keep crushing to a point. But the time at which the star reaches the horizon radius, its density is still very low.
Right.
And because the density is very low, people thought that no new physics can happen there. Because at low density, we think we know all the physics. And that's the real problem, right? So now that I'm glad you asked it. Can I just take 1 second to show the density is low? I'll come back to your questions in a minute. So suppose you have a star of mass m, then let the density of that be rho. Then what is the radius at this point? Rho times r cube is like m. I'm not doing the 4 pi by 3 and all that, but that's how you do the mass. Okay? And then I want gm by c square, well, 2gm by c square equal to the radius, the horizon. I won't worry about the factor 2. Okay, so let's not worry about the 2. So if I write down what is m here, m goes like c square r over g. Is that right? M is c square r over g. I'm not putting the 2 in there. So if I put this equal to this, then I find that the rho, at the time the star is at this critical radius, goes like c square over g r square. Okay. So if I take a very big star, okay, the rho at the time when it is crossing that horizon is very small. Actually, it's better for me to write in terms of m. So if I write in terms of m, then rho is like c square over g. What was my r? R was gm by c square. So I'll put here r was gm, so g square m square over c fourth. So the constants are what they are. Let's not worry about the constants. But because the m is in the denominator, if I start with bigger and bigger stars, the rho, the density of the star at the point it's crossing the horizon radius, will keep becoming as small as I want. And that is really the essence of the black hole problem. You can choose as low a density as you are comfortable with. I put 1 gram here, and 1 meter away I put 1 gram. and then maybe 1 gram 1 meter away. So I make a cubical lattice of 1 gram at each point. And if I keep making it lattice bigger and bigger and bigger, at some point, it will become this situation. And you say, okay, that's my star. And then at that low density, 1 gram here, 1 gram here, you think obviously nothing new can happen, no new physics. And then it's in here. And then the light cones are inside. It has to go to a point. Everything is normal. And because densities are so low, when it goes through the horizon, it leaves behind empty space. So this will, as Shimit was saying, this is the crucial assumption. Is this region just normal empty space? Is this normal space-time? And so the whole debate about what happens to the black hole really focus on that. In the classical picture, the hole just goes through the horizon radius with no difficulty. The star goes through the horizon with no difficulty. If it leaves behind empty space, you're in deep trouble. Because if you leave behind empty space, in empty space, we know that this kind of pair production mechanism happens. That kind of pair production, that's the property of vacuum fluctuations of empty space. If this was not empty space, but some other kind of mess, then the Hawking argument will not work. So we'll have to always come back and focus on this question. Can you get there something there which is not empty space? Okay. Yes.
Always the other, I wouldn't call it assumption, the property of quantum field theory that any state at short distances looks like a vacuum.
Yes.
Is that also crucially used here, or does it follow?
So it's actually not really used here. So sometimes people mention what's called the Transplanckian problem, that if you keep asking for where these pairs are coming from, which we will see in more detail when we start doing the more precise calculation, it seems they are coming out from very, very short distances, which are maybe even smaller than Planck length. And then you can say, do we really know that that's what physics should be doing because we don't understand the Planck length? But actually, there's a way to phrase this entire argument which doesn't need anything to do with the Planck length, with no Transplanckian issue.
Yes, I was actually not talking about Transplanckian issue.
Okay.
Using the fact that in general quantum field theory, if you look at very short distance properties, they are mostly the vacuum properties. I mean,
Yes, yes.
Transplanckian is there because I think it's saying that there are high frequency modes, but the
Yes.
vacuum is full of high frequency.
Yes. Okay.
I'm just using that fact. Could there be something which tells you that's actually not true at the horizon?
Yeah, so it's important that the argument does not use that. So you can phrase the argument in such a way, and since you mentioned that, just remind me to mention it when we come there. You only, suppose you take a solar mass black hole and you make that as your example of the one which we'll use for the information paradox. You only need to be sure that your understanding of quantum field theory works from, let's say, 1 meter to 5 kilometers. The horizon radius is 3 kilometers. So from, let's say, 1/10 of that to, let's say, 10 times that. That's the only domain where you need to know what the physics is like. You don't need to know smaller, and of course, bigger than that doesn't matter. Okay? So that's very important, because you can always say there is something about short distances we don't know. The only thing you assume about short distances is that the vacuum is unique. So what that means is the following. If I say this space is empty, like we are trying to distinguish empty space from non-empty. Suppose it is empty. Empty means no stress tensor. And then suppose I ask for the evolution of a long wavelength mode, 1 meter. Take a 1 meter wavelength. And suppose it evolves to this, some kind of evolution. The theory has to be unique. That is, if I give you this mode at this time, at a later time it has to go to this if you are in the vacuum. If you say, no, there are two different vacua which differ at short distances. In one of them, this mode goes here, in the other one, it goes here. Then you can do a lot. But if you do that, then you can't predict anything. You lose predictability. So vacuum being unique is the same as saying the theory is predictable at low energies. So if you have predictability, the theory actually makes sense. Then the details of the vacuum don't matter, because the only property of the mode we will use is how do they evolve from 1 meter to 5 kilometers. We don't need smaller than that. Yes.
Basically, statement of effective field theory, right? So,
Yeah.
That we don't really need to care about what's going on. You impose some cutoff.
Yes.
Now, these modes are continually being drawn up out of some short distance theory.
Yes.
to scales that are below the cutoff. And so the reason you can do that is that there's no structure below the cutoff. Everything
Yes.
is in its ground state.
Yes.
And so you didn't really need to care about any
That's right.
details of that structure. All
Yeah.
you need to know is that as those modes cross into the domain where you're describing them in your effective field theory,
They should become normal modes.
they should come out in their ground state.
Absolutely. That's what you're saying. And actually, we have experimental evidence of that, because if you go back to the time of inflation, at the start of inflation, our universe was like the size of a marble, about 1 centimeter. Okay. If you ask what a Planck size mode at that time, how big is it today? It's about the size of a nucleus. Okay. So we have actually, and nuclear physics we know, right? We can go much below the size of 1 Fermi. All the things we do at the LHC and so on goes about 1 GeV, so like 6 orders beyond that, right? We go to several TeV now. So we can probe distances much shorter than what was 1 Planck length at the time of inflation, from the start of inflation. So we know that as space stretches, it creates new modes which are exactly in the same ground state, just normal vacuum mode. It's not like there's some magic hiding at short distances so that when you stretch space-time, some kind of animals come pouring out that you don't understand. So inflation is sort of a proof of that if you really believe in inflation, then the modes which were trans-Planckian are now well in the domain of nuclear physics. Okay. Good. So these are exactly the kind of thing which are going to be very important when we start debating this stuff, right? When we start seeing where could we be wrong in the argument, this is exactly what will come in. Okay. So let us now see where the problem is, because so far we don't have a problem. We only have an interesting process that if you have a black hole, then quantum mechanics makes it evaporate away by this very simple process, and that's it. Okay. But let us see where is the problem. Okay. Yes.
Singularity issue, right? Like, so this assumption, to just come
Yes.
to this, there's an assumption that it evaporates completely. What's the argument that it evaporates completely when it's...
So I'm glad you asked that, because there is no argument.
Okay.
So what happened was that Hawking said the black hole evaporates completely because he saw it was evaporating. So he said, what if it's going towards zero, it might as well go away. And I'll give you a slightly stronger reason in a minute, because when I give you the length scales, it turns out as you get closer to small, as the black hole gets smaller and smaller, it actually evaporates faster and faster. So it looked logical to Hawking that the guy completely evaporates away. But then because of the problem which I'm going to mention, which I haven't mentioned yet, people were not happy with that outcome. And so people changed this endpoint to saying that once it becomes as small as 1 Planck length, and then we really don't know what's happening, maybe it stops evaporating for reasons that we don't actually understand. And so that is called a remnant. Okay? I will talk about remnants in a minute. And it's good you brought that up, because actually a large part of the GR community actually believes that's the right answer. Just end at the Planck scale and it's all there. And what that means is that all this stuff which was in the black hole at mass capital M and all the other particles that fell into it, they're all hiding in this Planck mass remnant. So now you have to see how to make that remnant and so on, and there are many models, but that is an alternative to what Hawking said. But since I was mentioning Hawking 1974 paper, he actually said the black hole goes away completely, and then he just gave you the radiation. But the other alternative is there. But you have to say that the physics is changing in some way, because it was evaporating. If you say that quantum gravity comes in and changes this logic, then you can say whatever you want. So that's what people did. More questions? Okay, so I'll take something off the board now because I need to create place. So I guess I might as well just remove anything. So now let us see where the problem is. So all this was in 1974, but in 1975, then Hawking wrote the paper which really made him famous, and that was the information paradox paper. Okay. So what is the problem with all this? And the problem is, we again go back to that picture which had the electron and positron coming out like a pair. Then we actually have two choices. This is my mass m, this is my radius, and I said the E minus is here and the E plus is here. But I could also have it the other way around, because I could have this evaporation with the E plus is inside and the E minus is outside. Okay, they are both equally likely, so both possibilities are there. And so you can ask which one happens. And the answer is actually they'll both happen. It's quantum mechanics, everything is probabilistic. And so if you actually do the calculation, you will find the answer is a little bit like the following, the state of the pair. If I try to write the state of the pair here, I'll call that psi of the pair. It will schematically look like 1 by root 2. You can have E minus inside and E plus outside, plus E plus inside and E minus outside. Does it make sense to everybody? The superposition of two possibilities. This can be in and that can be out, or that can be in and this can be out. They happen with equal probability, so the relative coefficient is 1. I just put the 1 by root 2 to normalize it. So of course you have seen states like this before, like if you have 2 electrons and you want to make a singlet state, you take up times down minus down times up. It's the same kind of thing. Okay. So states like this are what are called entangled states, and they're entangled in the sense that if you ask what is the state of the particle, that question doesn't have any answer. The outside particle is a... So if I ask you what is the state of the particle which is outside, that is it electron, is it positron, the meaning of an entangled state is that that question doesn't have an answer. The outside guy is positron if the inside guy is electron, and the outside guy is electron if the inside guy is a positron. Okay, so that's how all the entangled states always work. Even if you have 2 electrons making a singlet, then this electron is spin up if that guy is spin down, and this is spin down if that guy is spin up. But if you just ask what's the state of one guy, the question doesn't have any meaning. But nothing wrong with that. You have entangled states in quantum mechanics all the time. So this is okay. There's no problem with it so far. But that's the nature of the state. So what happens when many particles come out? This was for one particle, but then this guy goes in, this guy goes out, then this, after some time, this is inside, this is outside, then one more pair comes out, then there'll be 2 particles outside, 2 particles inside. So then more particles outside, more particles inside. So we really have to write the state of everything. So let's try to see what the whole state will look like. Let's try to write that schematically. So maybe I will take this off now. So then I will write it like this. The total state will be like this. I'll write 1 by root 2. Then I have E minus in for the first pair, E plus out for the first pair, plus E plus in for the first pair, E minus out for the first pair. I wrote the same thing as before, but this is the first pair, right? First pair means this guy fell in, this guy went out, but after that another pair is going to be created. And so the whole state will just be multiplied by, so we just write tensor product. When you have 2 sets of particles, just multiply the states, right? 1 by root 2, and you will have E minus in for 2 for the second pair, E plus out for the second pair, and then plus E plus in for the second pair, and E minus out for the second pair. So it looks a little long to write down, but I haven't done anything deep. If you had 2 pairs of electrons, each making a singlet, you simply multiply the 2 wave functions, so the whole wave function looks like this. Okay. So this state is actually even more entangled than the previous state, because now the number of possible states of the particles outside, there are now 2 particles outside, and they have 4 possibilities. They could be electron-electron, or electron-positron, or positron-electron, or positron-positron. There are 4 states outside. And there are correspondingly 4 states inside, but for every state outside, its opposite member is inside, right? If there are 2 electrons outside, it's 2 positrons inside, and so on. So now the whole thing, if you expand this, there will be 4 terms in it. And so the full state in general will look like the following. The full state psi will be of the form summation I is equal to 1 to the power 2 to the n. If I go 3 steps, there'll be 8 terms around. You can probably see that easily. And there will be some state psi I in and psi I out. And there will be some normalization constant, 1 over 2 to the power. That's the normalization constant. So can everybody see the state will look like this? Because just like here we had two terms in the sum, you can call this the first psi1 and psi1, and you can call this psi2 and psi2. And so now there'll be 2 to the n states like this. There could be electron, electron, and then this will be positron, positron, this could be electron, positron, this will be positron, electron. And so there will be 2 to the n terms in the sum, and so the state will look like this. So it's not something inside times something outside. It's actually something inside times something outside, plus something else inside times something else outside, and then something else inside times something else outside, and you are doing it to a lots of number of terms. Okay? So these states, as we said before, are called entangled states. So what is a non-entangled state? A non-entangled state is just some psi in times some psi out. That's a not entangled state. But the moment you have something in, something out, and then you add another piece and another piece, it's called an entangled state. And the more the number of pieces, the more entangled the state is. Okay. So again, you don't have to know much about all this entanglement mathematics. All we need to know is that if there are more terms in this sum, we just say the guy is more entangled. Okay. And so the number of terms in the sum is this number here is 2 to the n. If you emit n particles, there are 2 to the n terms in the sum. Then the measure of entanglement we use, again, the number will not matter to us, but it's called S entanglement. It's called entanglement entropy. We don't need any reason, anything to know about it, but I'm just writing it just because people write it down. It's going to be log of the number of terms in the sum. So if you have 10 terms in the sum, the entanglement entropy is log 10. Okay. So this time, because there are 2 to the n terms in the sum, it's log of 2 to the n, which is n times log 2. So it's just to say that every time you emit more and more particles, the entanglement between the radiation collecting outside and all the stuff which is falling in the black hole, the entanglement keeps going up and up. Okay. So people plot this in a graph, and the graph is called the page curve. And again, we don't need to know these words for anything, but you must have heard the word page curve coming up if you have been reading any papers on this topic. So the page curve just tells you that as you keep having more and more emissions, so as a function of time, if you want to plot how much entanglement you have, in the beginning there are no particles outside, so there is no entanglement. But then the entanglement keeps going up and up, and so the page curve just keeps going up and up. So this is simply telling you that the entanglement just keeps growing, but it's just a description of the process. Right? There are more and more states outside, and the corresponding partner states are inside. If the outside states were electron, positron, electron, then inside will be positron, electron, positron. So but there are many terms in the sum, and so the states look like that. But now you can see where the problem is going to come from. For that, we can just look at just one of the states. Don't even worry about all the particles. Even if you had one particle like this, one pair of states entangled like this, or you could even think of something very simple. Just take the singlet state of 2 electrons, which you write like this. Is this familiar to everybody? If you have 2 entangled electrons in a singlet state, the first is up, the other one is spin down, minus this guy is spin down, this guy is spin up. So if you have 2 electrons in the world, this is electron 1, this is electron 2, electron 1, electron 2, then you can write their spin state like this, and this is an entangled state. There's nothing wrong with this. You can take these electrons, you can put them as far as you want, and you can have an entangled state, and that's still fine. You actually make this in the lab very often. You make 2 electrons in a singlet, you take 1 electron far away, there'll still be 2 entangled electrons. Nothing wrong with that. But now the funny thing is, suppose 1 electron disappears from the universe. Now how can electron disappear? Normally electrons don't disappear, but suppose it did disappear. Then you can ask, what is the state of the other electron? And now the point is that electron doesn't have any state, because its state was actually conditional on this guy. That guy was spin up if this guy was spin down, that guy was spin down if this guy was spin up, but if this guy is not even there, then that guy doesn't have any state at all. Okay? So then this guy has no state. I'll put a question mark and just write no state. So this is actually a big problem. In quantum mechanics, if you have 2 particles which are entangled, up to there is no problem. One member can be very far away, that's still no problem. But if somebody tells you that the other guy doesn't exist anymore, there's a serious problem, because there's no way to write the state of the particle which is left. The 2 things together had a state, by itself, nobody had a state. And so now you can see that's the problem with what Hawking is going to face, because Hawking, I erased that here. In Hawking's situation, he has all this radiation which came out, And in the end, there was nothing left here. The black hole is completely gone. So all these particles are entangled with something here. But if this thing is gone, then I have that kind of situation where I had two electrons entangled with each other and one of them has disappeared. Now this radiation has no state. So I'll put a question mark here. And that's very funny. You have some photons in your hand or whatever radiated out here, electrons and positons, some particles in your hand, and there is no state you can write down for those particles. Now normally everything should have a state. The state could be entangled, it could be this with somebody together makes a state. But if there's nobody else, this is the only guy left, this guy has no state. And so Hawking was very excited and he said that black holes actually violate quantum mechanics. We should give up quantum mechanics because now when you have black holes, you will have things which have no states. So you should actually start with a bigger theory which has lots of quantum mechanics, ideas of entropy, thermodynamics, loss of information, randomness, everything mixed in, and you should start from scratch. All of quantum mechanics is gone. Okay? So you can see that's a very serious problem, and that's what's called the black hole information paradox. Okay? So because now we have reached the crucial problem, so let us just summarize all the steps, because now we'll go back and try to make the steps more precise, and then at the same time we'll invite you to see which step you think is going to break. Because if we don't break any step, we have to give up quantum mechanics. Okay? So let's just review our steps. Let me see if I have saved anything on the board which I can use. So I don't have anything here. Maybe I rubbed out a lot of things, but just remember all the steps. First, you have a star which stops burning. It's going to shrink. Even at very low density, it's going to go inside the horizon radius and it's going to make the black hole. Once it goes inside the horizon radius, light cones turn inwards. It has to go to a point. So you're definitely going to make the black hole. If you can't find a way around that, you've gone past the first step of Hawking. Somebody had a question.
Hello. Should we think that this stem of mesmer entangle just a low angle approximation or two-level approximation? So in this sense, if we include the back radiation, the mesmer entangle stem will be fair.
Good. Let me try to repeat your question and see if I understand. You're saying this is all a leading order calculation?
Yes, because we just consider two level, but indeed we should have an infinite level. Is right?
Yes, we should be more accurate because there can be subleading corrections.
Yeah, but there is also a low angle approximation. In this sense, if we include the back radiation, then we should include the more mode, not just the two level. So in this sense, I will think that this mesmer entangle statement may be changed by the back radiation.
So that's an extremely important point, and that's what actually confused a large part of the community for a long time. Okay, and so when we talk about it, the later steps of this discussion on the second pass and third pass on the problem, we will see there is something called the small corrections theorem, which actually proves that any small correction to this, which can come from higher order effects or some effects we don't even know, they will not change the conclusion. So that theorem is very important, because if there were some small corrections which we have forgotten here, then somebody could say because of that, and the back reaction is again a small correction of that kind. Okay. But I'll tell you the nature of the small correction you can add. It's completely generic. With whatever is allowed for the small corrections, this page curve we drew will actually keep rising. That's what the theorem tells you. So until you add in the small correction theorem, there's a gap here. So when we make the thing more precise, as we are going to do, we will have to come and talk about that. Good. Okay, so let's just review all the steps where we are right now. So first step, let me just draw the steps here, and then I will ask you, which step do you think you want to break? And this was certainly one logical step. So the first step was that the star is collapsing and the light cones go in and the star goes all the way down to a point. Okay, so that's, let's call it step A. Here the problem was this goes inside the critical radius at very low density. So you have to somehow find a way of changing low density physics if you don't want this to happen. Okay, so that's your first problem. Suppose you can't change low density physics and this happens. Then you already have your black hole. Then the next step was that you get all this pair production. But that is just the physics of vacuum fluctuations. It has already been tested in the lab in other cases. And actually the same vacuum fluctuation, we are going to do the derivation of that a little more precisely right now. But it turns out the same physics which gives rise to these fluctuations is responsible for the creation of the perturbations in inflation. Exactly the same physics. Okay? And that we see because the perturbations of inflation, they give rise to large-scale structure, which gives rise to galaxies and stars, which ultimately give rise to us. Right? So you can say all that is observational evidence that all the physics of this, which is just normal QFT in curved space, we have so much evidence for. Anyway, the argument for this is very robust. I'll just show you the argument. It's very robust that you get the pairs. If you get the pair, then you'll get all the radiation, and then you have to talk about the fact the argument keeps working till the hole becomes very small. Very small means how small? Well, as long as quantum field theory keeps working, Hawking's argument keeps working. The only way quantum field theory might fail is if this thing becomes Planck length, because then quantum gravity comes in, and you can say maybe you don't know what happens. So then you can say when it becomes quantum gravity, there are two choices. Either it just stops here, then this is called the remnant, or it completely goes away. This is what Hawking did. And then you have a paradox, or that's a failure of quantum mechanics. So that's it. That's the entire puzzle. So now different people you can see started taking different choices. Okay. People could not find anything wrong with this. This also, the argument is, calculation is very simple. I will show you a little bit of how it's done so that people could not find anything wrong with. So most of the GR community, see, Hawking of course was very happy with this. Some other people like Bill Unruh are happy with this. Okay, who wants information, just throw it away. Okay, but most people were not happy with that. So then they chose this scenario. But there is a problem with this. So what is the problem with this? It's called the remnant scenario for obvious reasons. So this remnant has Planck length size and also Planck mass, because when the black hole becomes Planck length, if you put everything in the formula for the radius, you'll find also has Planck mass. So it's very light, almost no energy in it, and almost no volume in it. But actually it has a lot of states inside it. How many states are there inside it? Well, all the mass m, the star, that's hiding in there. Remember, all the star went in there. And then all the electrons or the members of the pair, every time you create a pair, one member goes inside, one member goes outside. So the member inside, all those guys are also there. I'll just draw them with dots. They are electrons, they are positrons. Those guys are also there. The only reason their mass is so small is because of the negative sign of the gravitational potential. Remember that story. It's because of the negative sign. But they're all in there. And so how many states are in there? Whenever you entangle two things, when you write a sum like this, if the guy outside had 2 to the n states, the guy inside also has 2 to the n states. You remember what the states were, right? There were electron, positron, all the different orders of electrons and positrons, and the mirror of that was in the inside. These were electrons, these were positrons. So there are 2 to the n states here. So there are 2 to the n states here, even apart from all the states of the star. But how much is n? Well, that depends how big the black hole was. Because n is the number of particles you emit till the black hole finishes. But if you start with the black hole bigger and bigger and bigger, the n will be bigger and bigger and bigger. So the number of states you have to put in the remnant is actually infinite, because the remnant can be coming from a star of any size. Okay, so remnant has infinite degeneracy. The infinitely many states of a Planck mass object in Planck volume. So if you try to do that, it's actually rather problematic.
Basically, the exponential of the entropy of the radiation which has gone out.
It's the number of states of the radiation. Like we actually counted all the states of the radiation here, right? They were just the orderings of E plus and E minus. You take the log of that, you get the entropy, you exponentiate back, you get the number of states. That's exactly what it is. Right? So if you have that many states in there, how do you put that many states in that much volume? In a normal field theory, you actually cannot do that. And the reason is that in a normal field theory, one cell of phase space of volume h cube has one state. People remember that from quantum mechanics? So if I give you limited volume and also limited energy, you only have a finite number of states possible. If I give you limited volume but unbounded energy, you can go to higher and higher wavelengths. You can put as many states as you want. If I give very little energy but a lot of volume, you can put lots of low energy photons, you can get lots of states. But if I limit both your volume and your energy, you can't do it.
Well, of course, the way this makes that is that it might look like it's not very big from the outside, but in GR, it's very big on the inside.
That's right. That's why in a field theory, you can't do that. In a field theory, you can't do that. But when we actually see what's happening in the black hole in little more detail, when we write out the Hawking calculation a little more precisely, it turns out because space and time interchange roles inside the horizon, there's actually a lot of space inside the black hole. So it is possible to do that. But there's actually a very good reason why a lot of people think this cannot be possible. Even though you can make a model to do that and all the GR people are happy with it, people who do string theory are not happy with it. Because in string theory, you can actually rule it out immediately. And the reason you can rule it out is that in string theory, you have something called ADS-CFT correspondence. Now, I know that not all of you here would be string theorists, but could I just ask how many people are familiar with the ADS-CFT correspondence idea? Okay, so maybe just one or two. I'll just say it, but you don't have to use it for anything else. But let me just mention what the issue is. So, if I have gravity in some region like this, I can call this is time here, and this is the radial direction. Then this is called the boundary of that region. I'll draw the boundary in a thick way. This. And so if you want to do gravity in this region, you actually write that same gravity theory in terms of just an ordinary field theory on the boundary of that region. So that's called the ADS-CFT correspondence. But if you look at the CFT here, and suppose in the gravity you had a remnant. Remnant would be some particle of some mass lying there for all time. So I just draw it like this, particle trapped with this wall line. Okay. Suppose it had mass m Planck here, the Planck mass here. That corresponds to some fixed energy here, some energy in the boundary theory, some fixed energy. And then if the number of states is infinite, I need an infinite number of states of that field theory at a fixed energy. But the field theory in this case is just an ordinary Yang-Mills theory with some finite value of the number of colors n and living in a finite volume, which in this case you can just call 1. And so what happens is that the field theory has only a finite number of states if I look for all the energy below Planck energy. Okay, so if you have ADS-CFT duality, which comes from string theory, you simply cannot have remnants. Okay, so now you really have a problem. If you're a GR person who says,
Sometimes people say that this clearly cannot happen for ADS black holes, but if you have asymptotically flat black holes, who knows what exotic dual it might have. It has some dual, but it's not, not the local quantum field theory dual. So maybe weird things can happen there.
But I think there is a way to, so that's an interesting part. I hadn't actually heard that argument, but I would like to go around it maybe in the following way. Just take a near extremal black hole of the kind we are very familiar with. And then you can do the story with it, feed mass in it, take it out and so on, and make the entanglement as large as you want, the usual story. And now you have the remnant scenario required. And now you have the guy sitting, the near extremal black hole is sitting nicely inside an ADS region. And you'll be forced to the conclusion this guy has an arbitrary entropy because you can keep doing the Hawking process of feeding and evaporating, getting unbounded entropy. And this remnant sits deep inside an ADS region. Yeah, it doesn't do with the fact it's attached. It's all something to do with this guy itself. This guy sitting inside ADS, for every near extremal black hole, that's exactly how it is. Okay, good. So then remnants are okay for all the GR people. Also, GR people really love that. They hold on to that for dear life. That's all that they like. But then they have to give up string theory because string theorists hold on to ADS-CFT for dear life. And then they can't have remnants. Okay. So now let's see where we are going to go from there. Because suppose you really believe in string theory, then the remnants are not allowed. So I'll have to cancel this out. In string theory, you also don't want to lose quantum mechanics because quantum mechanics is based on normal field. String theory is based on quantum mechanics. So I don't want to lose quantum mechanics. And so I have to give up this or I have to give up this. And that's the really interesting part of the story. And when we start talking about this tomorrow, I'll tell you how these things break. And we'll actually find that this one really breaks. That's what I would believe in string theory. But today, let me see how I'm doing for time. So, do people want to take a break if you are tired, and then we come back and do the proper Hawking calculation a little bit more detail? Or do you just want to keep going? Okay, yes.
May I ask a question before you start?
Yes, please.
So in the case of remnant, you mentioned about the infinite number of state in the remnant. If people consider tunneling of this state back to the environment, then you can reduce the severity of this problem.
No, absolutely. So you can talk about I just have to repeat the question because it's an important issue. If you have a remnant and everything is trapped there, then slowly you can leak things out, and then you can say that ultimately it's all gone to infinity like a normal radiation. So then everything looks okay. So this scenario is there. It's called a slow leaking remnant. And for example, if you talk to the people who do loop quantum gravity, their model really is the slow leaking remnant. But there is one constraint here. Because the remnant is very small, its mass is Planck mass, okay, it cannot evaporate very fast. It has to be slow. So why does it have to be slow? It has to be slow because you have to radiate, let's say, n quanta out. If we had trapped n quanta in, we have to get all the number of states out, you need n states. So you have to radiate a large number of quanta. So each of the quanta has a mass m Planck over n. So each quanta has very low energy. If they have very low energy, they have very long wavelength. If they have long wavelength, okay, you cannot emit all the particles at once, because suppose they are fermions. You cannot put two fermions in the same wavelength. One fermion has to leave, and only then the next one can start. Okay? Or if there were bosons, and you put two bosons in the same state, that only makes one state, but you have to radiate away 2 to the n states. So using this argument, you can set a bound on how quickly the whole thing can evaporate. Okay? So it actually can evaporate much slower than the time of Hawking radiation. It takes much more time. And the reason is that because the mass of the remnant was so small, each particle needs to have much longer wavelength. Okay? So because radiation is so slow, the problem with ADS, CFT and string theory remains the same. Because for all the time the remnant is not radiating, you need to have those states sort of trapped in there, and the field theory doesn't allow. So you have to really do the calculation of how quickly the remnant can radiate, and string theory will not allow you to hold a state in the Yang-Mills theory for that long. So normally a black hole of mass m radiates in a time of order m cube, but a remnant will radiate in a time m to the power 5. That's the problem. Otherwise, it was a completely good solution. And in many theories which don't care about ADS-CFT, like loop quantum gravity, this actually is their scenario, the slow leaking remnant. Okay, good. So I thought what I would do now is tell you a little bit more about how the calculations are done, because everything we have said so far is correct, but it's too heuristic, so you might wonder, do I really have to believe all that? And the first thing you might wonder about is the following. Let's draw the black hole again. And we said when we create a pair, one electron falls here and the partner goes away. So this guy is going away, so it's sort of gone. We don't have to worry about it. But this guy is sort of sitting in there, right? So the next time the next pair is created, suppose the positron is inside, the electron goes away. So this guy is gone, that's okay. But you can see these guys sort of clogging up this space, right? So you might wonder, after I do some number of emissions, suppose this space fills up with all these particles. Then the horizon region doesn't remain like a normal vacuum. We were doing this from vacuum pair creation. We assumed this region was vacuum, and that's how a pair would get created there. If the whole thing gets filled up with all these guys hanging out there, then maybe the process will stop. We have to worry about things like that. If you're doing the Schwinger process, actually that's exactly what happens, because you had all the protons here, and then the positrons went away and the electrons came here, and the electrons then hang around here, and then they start annihilating with these and other things start happening, and you get a whole cloud of photons here, but there's a mess here. It doesn't look like just the protons there anymore. So don't we have to worry about things like that over here? So let's go and talk a little bit more about the technical way this thing really works. And so we have to go a little bit deeper than all this schematic picture, even though the arguments we gave are completely correct, and the full puzzle is already there in what we said. So now let's actually write down the metric of the black hole. So far we didn't write down any metric, and the metric for the Schwarzschild black hole looks like this. I'm putting C equal to 1. Let me put also G equal to 1. Okay, so I wrote the metric, but maybe I should at least ask how many people are familiar with the Schwarzschild metric? Okay. Is this people have people take a GR course? Maybe the students, I actually ask the students. Can I assume this? If you don't follow this part, it's still okay, because you already have the puzzle. But if you do know GR and you know this metric, you can learn a little bit more deeper about what happens. So now if you look at this metric, there is something interesting about it. As long as R is bigger than 2m, this number is positive, so the dt square part has a minus sign, which is how we are used to dealing with metrics normally, and the dr square part has a plus sign. So for R bigger than 2m, t is a time-like direction, and time-like just means that this thing has a minus sign, and R is a space-like direction, which means this piece has a positive sign. But you can see that for R less than 2m, the role is actually reversed. The t is space-like, and the R is time-like. And so that's really the important issue about a black hole. This really defines what a black hole is, because if I try to draw it, the radial coordinate here, and here is R equal to 0, and here is R equals to m, and that side is R going towards infinity. So this is my horizon. And now I draw what is called a space-like slice. A space-like slice should be just like on which I can set up all my initial data. So let me try to draw a space-like slice. Then for R bigger than 2m, out here, the slice will look like the normal thing. I can just take it to be t equals t naught. Okay, that's what slices look like. But if I want to draw a space-like slice inside R equals to m, then the roles are reversed, and the slice will be more like, you can draw a slice like this, which is R equals R naught. Can you see that that slice with R equals R naught will actually be space-like? Because R equal to R naught means R is fixed, but t is changing, and when t changes, then this piece is now positive, so it's like a dx squared. It's a space-like slice. They have interchanged roles. And I didn't actually go into all the details of this, but I could have one of these things called the Eddington-Finkelstein coordinate, and the picture actually is all completely rigorous, but I won't go into those details. And so a complete space-like slice actually can be made like this. So that's the funny thing. In a black hole, outside a space-like slice looks like t equal to constant is all true, but inside it looks like R equal to constant. Okay. So now you see something very funny. Inside the black hole, how big is the space-like slice? If it was a star, if the space-like slice finishes at the center of the star, so it's as big as the radius of the star inside, but you can't, not any bigger. But here the space-like slice is actually infinitely long. So the infinite amount of space inside the black hole. Okay? And so what really happens is that how do I actually see all that evolution? We said one pair comes out, then after some time one more pair comes out. That is all schematic. Let us see where those pairs are in this picture. This is the proper GR picture of the black hole. So if I go to a later time where the next pair comes out, it will be t equals some t1, right? So I can do that. So I went to a later time. And then the next slice I can draw. So draw like this. So here, forward evolution is this way in time. This is space and this is time. Now this changed around. Here this was space and this was time, but inside, because of what I just said, this is space and this is time, so I can draw the next slice like this. Okay? So what happens is when you go from here to here, you find that the metric has changed. This slice and this slice are not the same. The later slice, can you see that it is longer than the older slice? It's just stretched. And so even though the black hole metric actually looks time independent, that's not really true. That's true because it looks time independent because here none of the coefficients depend on time, but then this part of the metric only describes the outside. when you continue it inside and look at the whole thing properly using the critical coordinates and everything, you find the metric of the black hole is always time dependent. And you can see it pictorially like this, because if you draw space-like slices, the later slices keep getting longer and longer than the previous slice. So actually the black hole metric is something which is always stretching near the horizon. And that's the key point. We'll understand the stretching in more physical way in a minute. But because the stretching, it's very much like in cosmology, where the universe is just expanding and expanding and expanding. And so very much like how fluctuations are created during inflation, it's the same source which actually happens here. And so that's how we'll see the particle pairs are created. We'll actually do the calculation Hawking did, at least understand how that calculation is done. But what happens is when you go from here to here, one particle appears here and one particle appears here. So the electron could be here and the positron could be here, and then they would be entangled plus, E minus, and all the same things we said. And then what happens at the next step, the slice becomes even longer. And this electron goes here, it just evolves here. This electron moves out here, the positron, because things outside are just floating away. And here a new pair is created, the new E plus, and here is the new. So these guys keep floating out to infinity. We never said there was a problem with that. But there's no problem on the inside either, because what happens is this slice keeps getting longer and longer, and the older members of the pair are here, 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 and then the new guy comes here. The area near the horizon where the new pair is coming, there is no one there. It's always the vacuum. It's always the vacuum, because this guy has gone off to infinity. We were worried about these guys, but these guys are all laid out on this slice which keeps getting longer and longer, and they're not hanging out near the horizon. Okay? That's very important, because in this rough picture we had drawn, I think I would erase the picture, where the electrons were just sort of collecting over here, they could soon choke up the process and stop it. But because of this, it doesn't stop. So this is just to say that every step we said before was not fully accurate, but really the essence was really correct. This is how it actually happens. Okay, let's now go and do one more thing with it, and then we'll really understand the full process, that the calculation that Hawking did. And that is to understand how, using quantum field theory, this vacuum fluctuations really come out. Oh, this whole idea that things just fluctuate and they become particles, all good to say, but can we actually see how it mathematically happens? So we'll do a rough calculation, but that calculation is actually fully accurate in the sense that if you just do it more precisely, it doesn't add anything to it. It will change you factors of 2, but all the essence of physics is actually here. So it's not going to be otherwise approximate. So for that, we'll go and look at one thing. I'll just draw the schematic picture again. Suppose you're in a black hole and you're in a rocket ship here, and you're trying to fly out of it like this. So let's ask, can you escape? Yes. If you're outside the horizon and you go very fast here, you can get out. What if you were on the horizon and you try to escape? Where will you go? Actually, you'll be stuck right there. You can't go anywhere. Do you remember this picture we had drawn? This was the black hole in the original picture. And the light cones here looked like this. And outside the light cones sort of look like this. So here, if you're going out, you can see you're escaping. At the horizon, even if you try to go out, this is the outward direction, this is the inward direction, you're still staying at the same radius. Can everybody see that? And if you're inside the horizon, this is the outside direction, this is the inside direction, but even the inside direction is actually going in. Can you see that? So here the outside direction is going out. The inside one is, of course, going in. Here the outside one is still staying there, but not able to get out. Inside one is going in. And here even the outside one, even that is going in, and the inside one, of course, is going even faster. Okay. So let's just draw that schematically. This is the line on the horizon, r equals to m. This is the outgoing ray I'm drawing. If you're just outside, you ultimately manage to escape. But if you are just inside, you ultimately fall in. Can everybody see that if you just do 3 guys all trying to escape outwards, if you're just outside the horizon, you will actually get out. If you're on the horizon, you'll stay there. If you're just inside, you'll ultimately actually be dragged back in and you'll fall in. Okay? So this is the full magic, because you can now see that such amount of spatial distance, after some time, gets stretched to this much distance. Can everybody see the stretching? So the whole physics is going to come from there. That if you have some space which is actually being stretched, then if you had the space which was actually empty here, it was a vacuum. By the time it gets stretched, there will actually be a pair of particles here. One electron, one positron will appear automatically. That's all that we need to understand. We need to go back and pull out our knowledge of quantum field theory to tell us that if we stretch some space like this, even if we had no particles here, one particle pair will appear here, and we will see that particle pair is entangled. If we do that, we have actually understood the actual Hawking process. No more arguing about uncertainty principle or anything. This is the actual calculation. Okay, other questions about this? Because this is the crucial step. Once we understand this, we are actually done. Okay, so when you stretch space, why do particles get created? So for that, let's go back and recall for ourselves what is quantum field theory. So in quantum field theory, let's take a scalar field. And if you have a scalar field, the simple way you can describe a scalar field, which you might have seen in textbooks or things like that, is you just take a bunch of mass points and you join them by springs. Are people familiar with this as a description of the scalar field theory? So if you just have a little point masses joined by springs, and then you say let me try to make a better picture. So I'll put a spring and a mass here, m, then a spring and a mass m, and a spring and a mass m. So I just have some springs here. So it's just harmonic oscillators here. And so if I excite, if this vacuum, all the oscillators are in the ground state, I have no particle here. This is my direction x. If they're all in the ground state, I have no particles anywhere. If I put this in the first excited state, I have one particle here. If I put this in the second excited state, I have two particles here. This is how you describe particles in quantum field theory. The only extra thing is there's a spring joining these particles. So the harmonic oscillators are coupled. And why do we do that? If I put a particle here, by exciting the harmonic oscillator, the excitation will go and start vibrating this particle soon, and then it will travel here, it will travel here, and that's how particles actually move. So if you just take a scalar field described by box phi hat equal to 0, you expand it in Fourier modes, and you literally see what that is doing in terms of creation and annihilation operators. You can actually model that by just having little harmonic oscillators all joined with springs, and that's a complete description of a scalar field. So you're not actually losing anything by writing this picture, even though it looks like you're playing with harmonic oscillators. It's actually literally a transcription of this guy. You have to take the limit of the size becoming 0, the lattice spacing, and then really have quantum field theory. So we'll just take that and we'll apply it here. So at this point, we had one oscillator, one of those springs, and here we had another one. So suppose I had two guys here, and the whole thing was in the vacuum state. So this guy was not excited, this guy was not excited. So let's just take 2 points. So I have one spring here, the mass point, one spring here with the mass point, and they're coupled. So I'll just deal with the problem. I'll forget all the other points and deal with the toy problem of two coupled harmonic oscillators. And because it's the vacuum here, I want the ground state of the two coupled oscillators. That's all I have to do. And then when I come up here, you can see the points have gone away from each other. So I still have a spring here on a mass point. I still have a spring here on a mass point. But because they are so far from each other, the coupling has gone away. Okay. So now all I'm going to do, I'm going to solve this toy problem of two coupled harmonic oscillators, the whole system in the ground state, and then I remove the coupling, and I ask what state do I get for the two oscillators. That is simply going to describe for me, if I have a scalar field, it's in the ground state, no oscillators excited, and then I stretch the space so the coupling breaks, they go far away from each other. What state do I get there? If the oscillators become excited, I have particles, because is quantum field theory, an excited oscillator corresponds to a particle. Okay. So this is the entire calculation. Now if you just do this toy calculation for a couple of oscillators, which I'll give you the answer for in a minute, you lose nothing compared to what Hawking did in his original paper. Okay. It's just the same thing dressed up further. So everything is actually here. So let's look at what this problem looks like. If you have two coupled harmonic oscillators, the Hamiltonian looks like a half. It is P1 square over 2m plus a half K1 x1 square plus P2 square over 2m plus a half K2 x2 square plus some coupling times x1 minus x2 square. This is the coupling between them. Suppose I gave you this Hamiltonian and I asked you to find the ground state of this. What does it look like? If I just had the two oscillators separately and I had no coupling, what would the ground state look like? The oscillator number 1 should be in the ground state, and oscillator number 2 should be in the ground state. If I didn't have this term, would you agree that's the lowest state of the system? 2 oscillators, so that's it. But if I actually have this coupling, and you then go and work out the actual ground state of the system, it doesn't look like this. Okay? It's a more complicated state, and if I tell you schematically, it looks like this. For the coupled system, the ground state actually looks like this. It's a simple calculation. You can just go and do it. You know how to do 2 coupled oscillators. You diagonalize the oscillators and you solve them, and you sort of come back and write them in terms of the original guys. Okay, so that's the ground state. So I'll just call that the vacuum state of the 2 oscillators. So it's a very simple toy exercise, and you compute that. And that describes to you the state of the quantum field at the bottom, because just a scalar field which is coupled oscillators in the ground state. And then as you go up here and they actually become decoupled, then this thing is gone. But if the decoupling happens fast enough, the wave function doesn't change. So you must have learned this in quantum mechanics. If you have some system and you suddenly change the Hamiltonian, the wave function doesn't quickly change. That takes time to change. So suppose the wave function doesn't change, but the Hamiltonian has changed. That term is gone. You still have the same state, because we just said the wave function can't change quickly enough. And so this is the state which you actually get for these 2 oscillators. And now there are 2 independent oscillators because the coupling is gone. But let's just look at what we have there. One part says you have 0, 1, and 0, 2, which means there's nothing here, nothing here. So there's some probability that nothing happened, which is fine. Nothing happened. There's some probability. But the more interesting part is this one. There's one particle here and one particle here, because if you excite the oscillator, you have a particle. And that's all that is happening. So if you actually go and just write out the scalar field in terms of, its actual A and A dagger modes, and then you just see what happens when you actually expand the space, this toy calculation actually captures everything that Hawking actually did in his paper. And so the time dependence that somebody had talked about before is actually crucial to the story. The metric may look time independent, but that's because it only describes the outside of the black hole. You write the whole thing we just saw from the pictures, the metric is actually stretching. You can see that if you write the outside and the inside, both the metric is actually stretching. The stretching is what is actually creating all the particles, because even if you start with a vacuum here, on this slice, you actually have a pair of particles. So can you see that the state we get on this slice here at a later time is actually an entangled state? So it's entangled because you could have the vacuum here, and then you'll have to, if there's a vacuum here, you'll have the vacuum here. And then if you had a particle here, you'll have the particle here. So you can see the state is automatically coming out to be of the entangled form. And this is the entire actual calculation of Hawking. So Hawking simply went and wrote down the scalar field and saw that when he evolves it in the background of the black hole, he actually went to the horizon and noticed that at the horizon, the different geodesics were separating away from each other. And then he wrote what happens to the Fourier modes here, and he saw they got stretched to different Fourier modes over there, just pulling apart. Then he did this calculation, maybe slightly more accurately than we have done here, but the conclusion doesn't change. You simply get entangled states. And now we have actually completed the loop, because this is the actual end of Hawking's calculation. And everything that we said before schematically was true, but the only 2 things we have picked up in this, making it more precise, is firstly that the inside of the black hole doesn't get choked up, because there's an infinite amount of space. You can see where the slices are actually coming and where they are going to, the particles. So pair production keeps going on. And how does the pair production actually happen? Well, this is the actual mechanism. If you just know a little bit of quantum field theory, you write this out explicitly as the Fourier modes, and the Fourier modes give you this as the particle creation. So this is actually all I want to tell you to complete the picture, and let's just have questions now. Yes?
Coupling term in the toy model seems to become large when x1 and x2 are separated. So
Okay,
after the space
no, actually it becomes small. So let me show you where this term comes from. So this one comes from the grad phi square. So if I write the Hamiltonian for this scalar field, the Hamiltonian looks like there's a momentum term pi square, and then there is a grad phi square. Okay, so let's write down the grad phi square. So the grad phi square is phi 2 minus phi 1 upon the distance squared. It's a delta which is changing. So delta was small here, so the C was big, let's say order 1. And when delta becomes big, the C becomes small. That's why it goes away. So it is two coupled guys going to two uncoupled guys because delta is in the bottom. Yeah. So I have some notes on this on the web. You can actually, this case I worked out fully at some point. And this is the toy model for the Hawking radiation. But this toy model is not missing any details. If you do this, you have the full calculation of Hawking.
This picture seems to suggest that, so at a later time when the space is stretched, you say that the coupling term essentially is dropped. So the system reduces to two decoupled harmonic oscillators.
Yes.
But then you said that the state is still the ground state of the initial Hamiltonian. So this means that at a later time slice, the state is no longer in the ground state.
Absolutely. Yeah.
Oh.
So it's because so let me just connect to the original picture, the picture up there, right? So we start with the vacuum on this slice. And then on the later slice, we drew these pictures before that particles appear, just a picture. If you now want to say what are those particles, what has appeared, if you look at a scalar field here, it has got excited, it's not in the ground state, it has got excited to the first level. There's one particle being created, exactly like we said. And because the oscillators here get excited, one particle got created there, right? And then we said, as you evolve to the next slice, this guy goes here, this guy goes here. But again, these two particles were close to each other, they were coupled oscillators, and then they become decoupled, so one more pair of particles come here. So that's what we were describing. So now we should just take what I was drawing there and put it in the context of this picture, and now you can see how the pairs are coming one by one on this slice. So if the field gets, if the harmonic oscillator here gets excited, that means there's one particle here. If the harmonic oscillator here gets excited, it means there's one particle here. And so you just take that two oscillator case and keep putting it in this context, and the full Hawking radiation comes out. Okay, so we don't have that much time because we are down to the last few minutes. So let us just see where we want to go from here and what have we done now. So what we had done before the break was we just laid out the entire puzzle in the following sense. We just said that if you just start with a star, which is all normal physics, and then you let the star just collapse and make a black hole, and then the black hole is going to create some particles. And now all the steps of Hawking's calculation are all just here. So nowhere have we used anything which is sort of unusual, because this description of scalar fields and the fact that scalar fields create particles when you stretch, this is what is called the physics of quantum fields in curved space. And this is the same physics which gives rise to all the creation of modes in inflation. So people believe this. And the same analog of this, which is done for the Schwinger effect, it has, people believe that too, because it's a very simple calculation. So there seems to be nothing to not believe about this part. And this part was one of the things I had drawn before when I said that once you have a black hole, do you actually get pairs? We have written that very schematically. And now we see this is all the calculation that goes into it. But this calculation is just very standard quantum field theory, so people could find nothing wrong with it. And so I must say that there really is no place to find anything wrong with this one. Because this calculation, all that it does is that in normal flat space, you try to solve the equation for a scalar field, box phi equal to 0. And quantum fields on curved space just say that if the space is curved, you should write the box operator in the metric G and solve this equation instead. So that has been something very standard. There's almost no choice. What else would you do? And if you do that, it gives you all the things like inflation and so on, which you believe. So this thing that in flat space, if you have box phi equal to 0, you should simply write the box operator in a curved space, and that's how you get quantum fields in curved space. That's the physics that gives you this, and is the rigorous version of what happens here. So in the 3 steps I wrote, the middle step was, once you have this, are you actually going to get the pairs? And I don't think anybody has ever found a mistake in that one. So now you're left with the other 2 places. Either this is not the picture of the black hole. Okay. And for that you have to say, why is it not the picture? Because it was made by just classical physics almost look like. Yeah. So either you have to question this one, you can question, but what I'm saying is this is just as simple as this, so nobody could ever find a mistake in this. See? But then the last thing I want to say in response to a question which came before is the whole issue about the small corrections theorem. And with that, the argument would really sort of close on itself. So we had plotted this thing called the page curve, and we draw the time here, and we draw the entanglement here, and we said that as we emit more and more pairs, the entanglement keeps going up because there are more particles outside, and the black hole keeps sort of becoming smaller and smaller, and the entanglement of these particles with what is left here, this entanglement, it just keeps going up. And that was the problem that we were having. Right? And so now people might wonder, the number of particles you emit, n, is actually very large, certainly much bigger than 1. So how big is n? N is of the order of the mass of the black hole upon the Planck mass whole square. So that's actually a very big number. So what people started wondering was, we had actually written the state of the pair. We wrote down the psi pair, which was of the form, we wrote something like this, right? E minus in, E plus out, plus E plus out, and E minus in. So this was the state of the pair. But there could always be some small mistake in that, and so you could have a small correction to it, which I'll call delta psi. And so delta psi is small, so its norm is, let's say, less than some epsilon. So that's always possible. You could always have some correction. It could be coming from back reaction. People also compute effect like if the particle which is leaving has a slight influence on the particle which is the next one coming out, they could slightly interact with each other, so that kind of effect. Or you could have some magical quantum gravity effects that you don't know so far, which could sort of automatically just make correct some quantum gravity effects. So there are many sources of small corrections because we don't know the full physics exactly. So suppose there's a small correction like this to the state of the pair, I'm always allowed to add this. This was Hawking's answer, and we just saw how it comes, just coupled oscillators, that gives this answer. See, we derived it here. But then there can always be a small piece which doesn't come from Hawking's calculation because from some new physics. And so now the worry is, because n is very big, and suppose epsilon is very small, but suppose epsilon times n is order 1. So make a small correction to each pair, but I have many, many pairs. So the effect could sort of accumulate with each other. And with that whole accumulation, suppose the curve doesn't go up, but finally ends up sort of coming down. And suppose by the time the black hole finishes evaporating, all this stuff is not entangled with this stuff. Can you see that then there is no problem? If this is not entangled with this, and this thing goes away, then this has a good state by itself. There's no problem. The problem is only if something is entangled with something and one guy goes away, then this guy doesn't have a state. But if this entanglement goes to 0, some graph is like this, then there's no problem because this guy can go away and this guy can just stay. So if there was small correction to each step that Hawking missed, because you have so many different pieces coming up, suppose epsilon times n was order 1, which can easily happen because n is so big, then epsilon can be small, and suppose that fixed this issue, then you could solve the problem. So many people have been thinking all the time through it that maybe the problem is as simple as this, that Hawking did a leading order calculation, and these would be called subleading effects because they are small. It's a subleading effect sort of because there are so many of them, because the n is so big. If they sort of collectively become bigger than the leading term, then maybe Hawking was just making a mistake and there was no problem at all. So at least that is a genuine worry. But the small correction theorem actually says that if at every step this is true, then the entanglement actually keeps going like this. So the entanglement, this amount that you can reduce is at most the change in the entanglement because of the small corrections upon entanglement is less than 2 epsilon. So if you make, let's say, the worry was if you make a 1% correction, but you're emitting 100 pairs, maybe the entanglement changes completely. But actually the theorem shows that cannot happen. The fractional change in the entanglement, if you make 1% correction, you can only change the entanglement by 2%. You can't change it all the way down here. So with that, the theorem becomes a serious problem now. Because now, as long as the picture of the black hole that you have, the classical picture, suppose that is approximately correct. Approximately correct means the Hawking process has to hold up to small errors. But small errors can't actually change your graph and bring it down. It's going to still leave you the same problem. And so now you have to find some other solution. Either you have to change the black hole picture by order unity and completely change the picture, or you have to believe in remnants, which means you have to give up ADS-CFT and therefore you have to give up string theory, or you have to find some other solution. So, okay, so that's what I want to say about the puzzle. Let's just have questions.
Or you can, or for gravity, you do something which looks like quantum mechanics, but not really quantum.
You can change the foundations of quantum mechanics. You can absolutely change I would say that if you're doing that, then it's also maybe going against string theory, because string theory is just based on quantum mechanics. So you would have to be not accepting the way we do string theory, at least.
But I mean, more like play some games with Euclidean path integrals, but it's not really quantum mechanics.
Yeah, so I'll try to talk a little bit about that tomorrow. This is the whole wormhole thing that has been creating a lot of noise and confusions. But it turns out that all those arguments are usually either circular, or they finally come down to, if you filter them out to see what arguments remain after you remove everything which is circular, one find that they are basically saying that there are non-local effects in the theory. So there is always one solution possible. I was going to talk a little bit about it tomorrow, but let's at least mention the issue. Suppose the black hole is like this, and all this pair creation happening like this and so on. But suppose there's some magical effect which can take a particle from here and straight put it out the black hole here. Then you can actually solve the puzzle.
Is that would characterize as departure from local quantum?
Yes, so if your actual gravity theory in its exact form is actually non-local, then you can do a lot of ways to bypass the puzzle. But I must say in string theory, we have never seen any evidence of such non-locality. So all these arguments with wormholes actually boil down to saying there's some non-locality that we so far have not found. So I would find that a little dubious, but in the end, that's what somehow they amount to. Yes?
Hello. Let's first assume that the black hole can be described by the quantum mechanically. And I want to ask, if now I assume that now quantum mechanics has a real eigenvalues in the Hamiltonian, but it's non-Hermitian, could I still have the patch curve?
The Hamiltonian is not Hermitian.
But the eigenvalue is real. Of course, I need to change the inner product space. If in this case, this quantum mechanics still has, we still expect this quantum mechanics system has a patch curve.
Yes, so I think if you start changing the assumption that the Hamiltonian is Hermitian, many things are possible. Okay, then things are possible.
Is it possible mean
so you could find some solution of the puzzle.
Puzzle means that it's unnecessary to have the patch curve.
Yeah, or at least you can change what the page curve looks like if the Hamiltonian was non-Hermitian. I have looked at a few of those models. I think what they amount to is in some way a loss of information.
I have one constraint here.
Yeah.
Eigenvalue of Hamiltonian still real.
Say again?
Eigenvalues of Hamiltonian still real.
Eigenvalues are still real.
So I have a constraint, not arbitrary.
Okay.
Yeah, it's one example. So do I still have?
It will be very nice to see an explicit model, because I don't have any good comment to make abstractly. But certainly there are models of the following kind. You take two vectors which are orthogonal at time t equal to 0. And then as you go to a later time, their angle becomes not orthogonal. At still later time, they become not orthogonal. And at some time, they become parallel. Suppose I do that. Okay. In a way, actually, that is non-unitarity, because in unitary evolution, two orthogonal vectors always remain orthogonal. So what you can do is you can evolve so that the vectors just become slowly more and more parallel, even though they were orthogonal to start with. I think if you do that, you can keep the eigenvalues real for some Hamiltonian, depends on the Hamiltonian. But with this, it is actually a way of doing Hawking's information loss in a gentle way. Hawking said at the last step, when the black hole disappears, all the information is gone. But if you keep doing this at every step, a little bit changing the angles, you sort of lose the information gradually to the end. So in a way, it still should maybe go under Hawking's category of information loss, because he was losing all the information at the last step, because all the states go to the vacuum. So many states go to one state. That's what unitarity loss is, right? Many states go to one state. They all go into the vacuum. Now, if you have two things, you gradually make two states go to become parallel, then two states have become one, but gradually. So it's a variant of Hawking's thing. And many people have actually made models like that. So many of these models made by Maxfield and so on, they actually do exactly this. They're basically non-unitary models. So that's certainly worth thinking about. But I think the string theory itself doesn't do that for you.
Yeah, but I just think the string theory now we only know the ADS background. But for DS background, I think what do you want to say? But it's for the DS background, but we do not know what is precisely for the quantum mechanics. So one example is that the quantum mechanics has real eigenvalues for the Hamiltonian, but it's not Hermitian.
So I think that is, for DS it's true that string theory has not been able to do anything good with DS so far.
Yeah, yes,
that is true, right? But the puzzle can actually be phrased in a very rigorous way in string theory, which I'll try to talk about tomorrow. That if you just start with Minkowski space in string theory, suppose you still want to stay with string theory, then you can make the Strominger-Waffa black hole out of strings and branes in a very rigorous way. You just play with that black hole, and you can make the problem completely precise, right? Because we understand everything about that black hole in string theory. And then let's ask the question in that context and ask which of these three possibilities goes wrong. Do you not make the black hole, or do you make the black hole and not get the pair production, or do you get the pair production and get information loss, or what happens? So because we can make the problem very precise there, I'll just start to talk a little bit about that tomorrow. But if you're not doing string theory, a lot of things are open. For example, if you just do ordinary GR, the remnant scenario is fine. So if you ask somebody like Bob Wald, what is the solution? He thinks that there are remnants. And he gives a model for the remnants like baby universes and so on. So but as we said, in string theory, you can't do that. But otherwise, that's allowed. Yeah.
So, something is wrong about this Hawking's original argument. At some point, it has to fail. At what point will the answers fail? I mean, there are some answers you get in the temperature of a black hole, entropy of a black hole. I mean, to what extent those are correct?
So I think those are going to remain correct, right? Because in string theory, we have got the entropy correct.
Yeah, that's why I was asking this question.
So you're asking, why is it correct?
Why is it correct?
So it's interesting that there's something I was working on last year where we showed that once an object is sufficiently compact, its radius is a star. It's not no horizon, nothing. But its radius is sufficiently close to 2m. It actually has to have the same S and T and everything as the black hole. So that may be the reason that it always has to work that way. We can discuss that separately, but that's the only answer I have. That once an object becomes sufficiently compact, its thermodynamics seems to become universal. There's an argument for that. But that's the only argument I know.
The black hole property would still be that it's on the surface, whereas for a generic object, I'm guessing it's not, right?
What would be on the surface?
Like your degrees of freedom are on the surface. Like, is there a distinguishing point?
Okay, yeah, so we should talk about that when we start tomorrow, because we have to get into the black hole thermodynamics, which I didn't do today. But it is not at all obvious where the degrees of freedom of the black hole are. Okay? So if you look at the entropy of a black hole, again, something we didn't talk about today, the entropy of Bekenstein is given by the surface area upon 4G. And that suggests that the degrees of freedom are on the outside. But he got this formula while looking at the standard picture of the black hole, where all the mass was actually sitting in here. And there was just a vacuum here. So there was no reason to say that they should be at the surface. It didn't make any sense, right? And that problem will persist. We don't have a good solution to that problem. Because until you understand the entire structure of this object, you can't actually see where the degrees of freedom are sitting. So it is not actually clear that they are really sitting on the surface. In fact, the model we get from Fuzzball is not clear they are on the surface, sort of they are all through, it's more like a star. So you have to understand why it goes to being like giving you the surface, and that's what I was saying in answer to Shimit's question. If you take a star, and you make the star whose radius is equal to 2m plus epsilon, and epsilon is quite small, there's a formula for how small, then actually its entropy has to follow this formula. So I can give you the reason for that, which I'm not doing right now. But So that's the answer I was giving in for what Shimon was saying. It's not because the degrees of freedom are on the surface. You can actually first prove that the temperature of this guy has to be the same as the temperature of this guy. And then you do thermodynamics like TdS equals dE. And if the temperatures of two objects are the same, then the entropy has to be the same. So you really have to ask why is the temperature the same. And maybe when we start tomorrow, if you ask me the question, just remind me, I can try to answer that question, how this thing came out. But it's very indirect as an argument. There's nothing very obvious as to why it had to be like that. But it's really, first the temperatures work out to be the same, and then everything else follows from thermodynamics. So why it's the area is still mysterious. It's a very good question. But I don't think there's any reason to say that just because the area, the degrees of freedom are on the surface. I don't think we've ever really found that. These are really deep issues that one has to explore with the question. They're really very interesting issues.
So if there is no